If you follow this tutorial step by step, then even if you have never ever designed any boards before, by the end of this tutorial, you will have this board. You will know how to design it. You will know how to upload some firmware on this board and how to bring it to life. In this tutorial, we are going to use this Easy EDA software and JLC PCB services. I need to say this video is not sponsored. Only the reason why we are going to use this software and why we are going to use these services is because they are simple to use and they are not expensive. Actually, this Easy EDA software is completely free. You just need to register, and you don't even need to install anything. This Easy EDA software runs directly in your browser, and this is the software which we will use to design our schematic and also PCB. Okay, so in this tutorial, you will learn how to design this schematic. I will also explain everything what we are going to do and why we are going to choose specific components. I will explain what you need to be careful about when you will be designing your own boards. And also, I will also explain how to connect everything together. So this can help you to understand what you may want to think about when you will be connecting components on your own board. Then once we have this schematic, we will also learn how to design PCB. Again, I will explain what you may want to think about when you will be doing layout, when you will be drawing the tracks, when you will be placing components. And once we design this schematic and board, this is how it is going to look. Then we will learn how to generate all the files which are needed to manufacture your PCB. We will learn how to generate all the files which are needed to assemble your board. We will send these files into production. If you like, you can do it too. And then once you receive your board, this is how it is going to look. Once you have your board, we will learn how to write simple software, how to upload it on your board, and how to bring your board to life. I really hope you will find this tutorial useful, and here it is. To design this schematic and PCB, we are going to use a website which is called Easy EDA. Just Google for this or search for this. Click here, register on this website, and then click on this Easy EDA Designer. The registration is free, so you don't have to pay anything. And also, you don't need to install anything because we are going to design the schematic and PCB directly in a web browser. Move cursor over File, New, left-click on Project. Name your project, for example, My Board, and save. Left-click on My Board project, be sure it is selected, and then File, Save. And now we saved this schematic page inside of our project. We are going to rename this schematic page. Right-click, Modify. Let's call it My Schematic. And we are going to add PCB. So right-click on the project, New PCB, Apply. Click on File, Save. Right-click, Modify, and we are going to call it my PCB. Next, we are going to have a look at specification of our board. And it's going to be very simple. On the board, we would like to have a microcontroller, RGB LED, accelerometer, push button. We would like this board to be battery powered, and it has to be really small. So let's start with something what is quite easy to add into our schematic. First, we are going to add this RGB LED. Go on JLC PCB website. Just search for JLC PCB. Left click. Then resources, SMT parts library. Here we can see the list of all the components which they can use for the assembly. And we would like to find LED, so go here, light emitting diodes. In this filter, we would like to only work with components which are in stock, and we would like to find RGB LED. Apply. There are only 3 options what we can use, so let's have a look on the first one. Left click here. Left click on download to see the datasheet. And this is not the kind of LED which we would like to use, because in this LED we cannot directly control the RGB LEDs. You can see this is a special diode which can be connected in series. So let's go back. I'm going to close this, open the next component, left click, open datasheet of this component, left click, and this is exactly what we need. Here you can see this is the component, this is the LED, and inside there are 3 LEDs. They have common anode, and then we can individually switch on or switch off these RGB LEDs inside of this component. Let's go back. We are going to copy the manufacturer part number. Just hover cursor here, left click, copy. Go back into our schematic. Double click on the schematic page. Go on library, left click. Here, Ctrl V and search for our LED. Left click to select. Left click on place. To rotate, press spacebar, and left click to place the LED inside of our schematic, press escape. Let's have a closer look at this LED. Let's talk about the things what you may need to think about when you are choosing components for your project. So first I'm going to click on this library, and here you can see the LED which we choose for our project. And what is important is this icon, SMT icon, which says assembled, because this means that when we will be ordering the PCBs and when we will ask this company to assemble, to fit the components, then this LED is available for this service, so they can fit it. You can see it also down here. They have these LEDs in stock. 380 is available for JLC PCB SMT service, so this is important. Maybe you don't want to use components which are not in stock, and we would like to be able to buy these LEDs in minimum quantity 1. This is also perfect, so we don't need to pay for, 1,000 pieces of these LEDs. When we go and when we have a look inside of the datasheet, there are few parameters which are important when you are selecting LED for your project. You may want to have a look on this forward current, which is 5 milliamps, and maximum is 10 milliamps. This is important because some LEDs, they need high current, 20 milliamps to light up. And for battery powered device, maybe we would like to use LEDs with low currents needed to light up the LED. So 5 milliamps is perfect. And also what is important is this forward voltage. For red LED it is 2.1 volt, for green 3.1, and for blue it's 3 volts. This is the voltage which is across the diode, and it basically means, for example, that you cannot power these LEDs with 1.5 volt because then they would not work. Okay, they need this forward voltage to work. It means we may need to power up these LEDs maybe with 5 volts, for example. In this case, in this RGB LED, is also quite important maybe to use this common anode, because when we have a look at the finished schematic, I'm going to open this finished schematic. Here you can see that we would like to control this ground connection to this each individual LED. So this is how you normally control LEDs, by connecting ground to LED, okay? If they would not have common anode, then it could be a little bit more tricky. You would have to use different circuit. So this is also perfect. Common anode is exactly what we would like to use. It means this LED is exactly what we would like to have in our schematic, and we can place another component. I'm going to open our specification again, and the next what we would like to place into our schematic is accelerometer. Let's go back to SMT parts library, click on all categories, and in sensors, motion sensors, accelerometers, check these in stock only components, and there are not so many. We would like to use maybe the cheapest one, so I'm going to have a look what is the price for one piece. It is $2.1 for this one, 4.5, $72, 12, 1.5, $1, 2.9, 1.4. So this is the cheapest one, and we would like to double check the datasheet. I'm going to close these datasheets which are here. This one and this one, we don't need them anymore. And I'm going to open datasheet for this accelerometer. Left click. Our board is going to be very small, so first we need to double check the size of this accelerometer, and it is only 2 by 2 millimeters. It's like 80 by 80 mils. It's very small. And because our board is battery powered, we would like to be sure this chip is or this chip has low current consumption, 0.9 microamp in standby. This is really good. We are going to power up this chip by 3.3 volts, and this is up to 3.6, so this is perfect. We would like to use I2C for communication because it's like super simple interface for communication. And also we would like to be sure there is an interrupt pin which can wake up our system. I need to search for this information, so I'm going to scroll down a little bit. This is the sensor, some powers, some other pins. The best will be just find table with pin description. It is here. You can see, okay, so this is address pin. This is just to connect it to ground or power. I2C serial data. Power, this is just this just needs to be connected to ground. This is the interrupt pin. This is perfect. This is exactly what we need. Ground, power, ground, and serial clock. Okay, this is super simple chip. It has everything what we need. Only what I would like to check is how this physical interrupt works. So let's search for motion detection or something like that. Motion interrupt. This chip has threshold interrupt triggered by internal digital wake-up engine. And the wake-up event can be programmed to be reported on physical interrupt pin. This is exactly what we need, okay? So this chip can basically detect movement, and then it will change the status of this int pin, and we can use it to wake up our microcontroller. Okay, we can use this chip in our schematic. Everything what we have to do is go back to this SMT parts library, copy manufacturer part number, go back into our schematic, library, Control V, search for this accelerometer. Be sure there is this SMT icon, left click. Be sure it is in stock. We can buy it in minimum quantity, one piece. Click on place, put it inside of our schematic, left click, and press escape. When we go back into our specification, next what we would like to place into our schematic is push button, and there is nothing really special about push button. When you go into SMT parts library, you can go to all categories, and here push buttons, tactical switches, you can find any button which you like, but I use this one. So if you like, you can use same, search for this number, and I use it because it is this kind of standard button. Copy this manufacturer part number, go into our schematic, click on library, Control V, search for this button, left click. It is available for JLC PCB SMT service, and minimum quantity 10. I need to be honest, I don't exactly know if it means that when we use their service, we have to buy at least minimum 10 of these switches. But I checked the other switches, and many of them, they have minimum quantity 10, so I really didn't spend much time investigating what exactly this means. It's okay. Click on place, left click to place this button into our schematic, and press escape. When we go back into our specification, only what left to place into our schematic is the microcontroller. So open the SMT parts library, go to all categories, embedded processors and controllers, and from all these manufacturers, we would like to use something simple. So maybe we would like to use something from ST Microelectronics or something from Microchip. I'm going to click on Microchip. Again, we would like to use only the components which are in stock. And from this list, many of these cores are a little bit more complex. We don't really need them. The simplest thing will be probably this 8-bit PIC microcontroller. But this is not the right one, because you can see there are not many, and this one is too big, 80 pins. We don't need 80 pins, we don't need 44 pins, and this is too small, 8 pins. It's not enough for what we need. I'm going to reset this, and I'm going to select this one. Okay, this looks better. Apply. There are still number of microcontrollers what we can choose from. So it means we can have a look on some low power support in a microcontroller, because we are going to use battery powered device. So ideally, maybe it could work with some low voltages, 1.8 to 3.6. Apply. and only one left. So let's have a look at this microcontroller. I'm going to open datasheet, left click. Scroll down, and we are going to check if there is everything what we need. But first we would like to check the size, because we would like to design something really small. The maximum width of the PCB should be like 1 centimeter for 100 mils or less. And the size of this microcontroller is 5.3 by 7.2 millimeter. It is like 200 by 280 mils or something like this. So it's going to fit. This is good. And we would like to check if there is internal oscillator, because we don't want to add any like extra components, and there is internal oscillator. This is good. 1.8 to 3.6 volt operation for this PIC 16LF part. PIC 16LF, that's the part what we are going to use. Sleep mode 20 nanoamps for PIC 16LF part. This is awesome. This is really good, because for battery powered device this is very important. Up to 17 IO pins, programmable weak pull-up resistors. This is also good, because then we can save space on some of the components. We don't need to add extra external pull-ups. Programmable interrupt on change pins. This is important because we would like to support interrupt for the push button, and also interrupt coming from the accelerometer. And we would like to have at least 3 PWM outputs for the LEDs to regulate the intensity. There are 2 in CCP modules, and it looks like there are also some eCCP modules with PWM support. So this should be fine. And we need also I2C interface to communicate with the accelerometer. It looks like there is everything what we need. So let's go back to this parts library, copy manufacturer part number, go into our schematic, click on library, search for this microcontroller, left click. 15 is available for JLC PCB SMT service, a minimum order quantity 1. Click on place, left click, escape. When we go back into our specification, you can see that we placed all the key components into our schematic. And now, what we are going to do in the next step, we are going to add the components which are needed to support these key components. And the first one is power supply. Go to SMT parts library website, all categories. We are going to search for power management IC, and probably the simplest regulator is LDO. So I'm going to click here, drop out regulators LDO. There are many different manufacturers, and for this kind of component I have good experience with Texas Instruments, so I'm going to select it, in stock, and we would like to use a regulator with fixed output 3.3 volt. Apply. This LM1117 is a very popular part, and we have them here, so that's what I'm going to use. It's not maybe the best component for battery powered device, but it's good enough for what I need. Click on download and open datasheet. We are going to find an example how to connect this chip, this regulator. I'm going to click here system examples, and here it is. It is super simple, just the regulator and 2 10 microfarad capacitors, one on input and one on output. go back to SMT parts library, copy the manufacturer part number, go back into our schematic, library, Control V, and search for the regulator. Left click, place, left click, escape. We would like to place also the 10 microfarad tantal capacitors, you know, these capacitors from the reference schematic. So in our schematic, go to library, left click on capacitors, left click on tantalum capacitors. Once you see the list of the capacitors, order it based on the capacitance. Left click here. Scroll down, find the 10 microfarad capacitors. And for this kind of part, for passive components, very often you can find basic parts. So here in this column, we are going to search or look for basic part. Basic parts are usually cheaper to fit on your board. Extended parts are a little bit more expensive. So if they have basic part for 10 microfarad capacitor, that's maybe what we would like to use. Here it is, basic part 10 microfarad. Now, very important, hover cursor over the capacitor and double check the voltage. You can see this capacitor is for 16 volts. That's perfect. That's okay for our application. So left click on place, zoom in, just use mouse wheel, press spacebar to rotate. Be sure the plus sign is on the top of the symbol, and left click, escape. To connect these capacitors, we are going to use this wire feature, this button here in wiring tools. So left click, zoom in, left click, left click, left click, left click, left, 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 escape. We would like to add also ground, so left click here, left click, escape. I will move it a little bit down, just press left button, hold it down and move it. And also we would like to add the power symbols. So left click, left, escape. Select this text VCC. We are going to change it to plus V in because it can be battery power. It can have all the kind of different voltages. And left click here. And this is going to be the 3.3 volt output. So let's put here plus 3V3, enter. We still need to connect these two pins. So let's have a look into datasheet what they say about this pin number 1 and pin number 4. I will go up and we are going to find the table with the pins. This. So in our footprint SOT223, pin number 1 is connected to ground. Ground this pin for fixed output option, that's exactly what we have. And pin number 4 should be connected to the output voltage pin for the regulator. In our schematic, we would like to place ground symbol to this pin number 1, escape, move it a little bit down. And we would like to connect this pin number 4 with the output, left click, left, escape. To connect battery to our board, we will need 2 through-hole pins or through-hole pads where we will solder 2 wires coming from battery holder. And the simplest and quickest way how to add 2 through-hole pins into our board is to put there a simple 2-pin header, which we will not fit. And that's what we are going to do now. Go to Library, click on Connectors, find the pin header and female header, order these components based on footprint, and notice how they name the footprints. Maybe we could use this to find our specific component. We don't have to scroll down. We can simply just write something like header through hole 2 pins, pitch 2.54, and we need vertical male. Search for this and scroll down, find the headers which are highlighted. This. Left click. And yeah, this could be the kind of header what we can use on our board. So just simply click on place, left click, and left click to place it into our schematic. Escape. Now maybe we would like to flip this connector. We would like to have pins on the right side. So left click to select, go to format, flip this symbol. And we would like to have pin number 1 on the top because that's usually plus. And we would like to have pin number 2 on the bottom because that's usually ground. So this is okay. Let's leave this header like this. For debugging and firmware development, it can be super useful if we provide alternative power source. And the simplest way how to power this kind of simple board is use USB micro connector. And that's what we are going to add next. Go on the SMT Parts Library website, all categories, connectors, USB connectors, and let's have a look what they have here. USB Type-C, we don't want USB Type-C. USB micro connector, this could be something what we could use. Copy the part number, left click, go into our schematic, library, Ctrl V, search for the connector, left click, left click, left click, escape. We would like to rotate the connector, so left click to select it, press spacebar to rotate, and maybe move it like this. Normally, you don't need to add like nothing super extra around this USB micro connector, but there may be some special cases when you would like to maybe connect these D- and D+ pins through some resistors. If you would like to know more, you can search for something like this, USB micro charging resistors. There are a number of websites on this topic, and usually you will find information something like this. For different manufacturers and different currents, you may want to use different resistor values and different resistor connections between these D+ and D- pins and the power and the ground. So just in case you may need this, what we can do, we can add some footprints on our board. And normally you will not fit these resistors, but if your special charger will require these resistors, then you may fit them later. Okay, so that's what we are going to do now. We are going to add some components around this USB micro connector, and we are going to connect it. Even we are not going to fit these resistors which are connected to D- and D+, we still may want to choose resistors with values what make some sense. So I will choose one of these examples which are here, and we will use this connection with 10K and 5.1K resistors. So first we will need to find a 10K resistor. Go to library. Be sure you have this JLC PCB assembled selected, so we only list the components which can be used for the JLC PCB SMT service. And search for R0402 10K resistor. Again, ideally we would like to use a basic component, so I'm going to click here, and it looks like this first one is the 10K resistor what we need. Click on place and just place it somewhere. Press spacebar to rotate and place it like this. Do exactly same for the 5.1K resistor. So go to library, search for R0402 5.1K, and let's have a look if they have basic part 5.1K. Okay, this is exactly what we need. Left click, place, and place it somewhere into schematic. Press spacebar to rotate, left click, escape. We need the same resistor combination also for the second D pin. You know, R1 5.1, R2 10K, R3 5.1, R4 10K, D plus, D minus. So I'm going to move this little bit up, press Ctrl, hold it down, left click also here to select them, Ctrl C, Ctrl V, left click, and we can connect them together. So left click, connect these two, escape, and place also ground here. Escape, move it a little bit down. Close to this V bus pin, we would like to place maybe 10 microfarad capacitor. You know, the 5 volt is coming through this V bus pin, and this 10 microfarad capacitor can help improve this 5 volt a little bit. It's not like the best and super proper way how to connect USB connectors, but in our application it is just good enough. We would like to keep it simple. So I'm going to copy this 10 microfarad, left click, Ctrl C, Ctrl V, and I'm going to place it maybe like here, escape. We would like to connect the ground here, and we would like to connect everything together. Zoom in, move this, maybe like this, connect D minus, connect D plus, connect D capacitor, one resistor, and also this resistor, escape. I'm going to make some space, so I'm going to move this down and all this a little bit here. I'm going to place here the +5 USB PowerNet symbol, so when we are routing these tracks, then we will know it is power. Just call it +5V USB, enter, connect it, and also maybe connect this shield to ground. So I'm going to draw something like this, and also I will connect this. Escape, and place the ground symbols here. You can use these, or you can just Control C, Control V. You can always select something existing and do copy and paste. We have almost connected this USB connector. Only what left is this ground pin. That's the simple one, but we also need to connect this ID pin. It can be sometimes a little bit tricky. If you would like to know more, you can search for something like this USB ID pin. And when I click, for example, on this link, you can find there information about all the kind of possibilities. So you can sometimes connect this pin to ground, you may leave it unconnected, or you can even like put there resistors with different values. And the very safe way how we can connect this pin is just use 0 ohm resistor connected to ground. And in case you will need to experiment with this pin, then just unfit the 0 ohm resistor, leave it unfitted, or you can put there resistors with different values. Okay, so in the next step, we are going to find 0 ohm resistor and we are going to connect it to this ID pin. I'm going to show you a different way how you can maybe search for resistors. So select existing one, copy the manufacturer part number, Control C, go to library, and we are going to search, Control V, we are going to search based on this number. We will just change it a little bit. So this was 5.1K. It means how we need to adjust this for 0 ohm resistor. We need to replace this with 0 and also this one with 0. Search. Okay, basic part, 0 ohm resistor, left click to place, left click, escape, and we can connect it like this. And Control C, Control V. Next, we are going to connect these two power inputs together. However, we cannot just simply connect this battery connector directly to this 5 volts coming from this USB connector. Because if battery is connected and also the USB cable is connected, USB power is connected, then they could fight together. For example, if the voltage on the battery is higher than 5 volts, then this power from the battery would like to go inside of this power supply on the USB. And also on the other side, if the voltage on the battery is lower than the 5 volt coming from the USB, then this 5 volt from the USB would try to go inside of the battery. And a very simple way how we can prevent this fighting is use diodes. And there is actually one special component which has 2 diodes in one footprint. I have used this component a number of times in my previous project, and that's exactly what we are going to use also now to prevent this fighting. So let's go inside of the libraries and let's search for this special component. Click on library and search for this. Left click, click on place, press spacebar to rotate, and left click to place it into our schematic. We are going to connect it. I'm going to make a little bit of space. I'm going to move this a little bit down, maybe like this. And also I'm going to move this. I'm going to select everything around our power supply, move it a little bit down, use the wire button to connect battery connector with the diode, connect USB 5 volts to diode, and connect it to our power supply. Escape. I'm going to name this net, so when we will be doing layout, we know this is important power net. I'm going to call it plus VBAT. Enter. I'm going to connect it. Okay, and we can also connect ground symbol here, maybe like this. Escape, Control C, Control V. How this special diode is going to help us? Why we use it in this circuit? How it is going to work, do you know? A diode is a component which can control how current is going to flow. So basically, when you have a diode, current can only flow from this side of the diode to this other side of the diode. And current can't flow from this side of the diode to this side of the diode. It means that, for example, the current from this battery, it can very nicely flow through this diode which is here, but it can't flow through this other diode. And same for the currents from this USB connector. They can very nicely flow through this diode, but they can't flow through this diode. So by using this special component, we prevented fighting these two power supplies together or power sources together. When you will be deciding on what kind of diode to use in your application, there are few parameters what you would like to double check. So when we open datasheet of this diode, the important numbers or important parameters for us is the maximum forward current, which has to be basically higher for as what we need for our board. 200 milliamps is high enough for what we need. And also what you would like to be sure this forward voltage is maybe as low as possible. That's the reason why we use this Schottky diode, because they usually have lower forward voltage than standard diodes. And this forward voltage is very important because this is the voltage which you will lose across the diode. So even if we have 5 volts, for example, here on this USB connector, you are going to use this forward voltage on this diode. So if it's like, I don't know, 0.5 volt for 100 milliamps, then basically here on the input of our power supply, we will have not 5 volts, but 4.5 volt when we will be taking 100 milliamps through this diode. Okay, and there is also another factor what you may want to consider. This voltage across the diode and the current going through the diode is going to change to power. So when you multiply the voltage by the current, then you will get power, which is going to be changed to heat on this diode. And you would like to, of course, you would like to be sure that this heat is not too high, so your diode is not damaged. Okay, so two important numbers, forward voltage and the maximum forward current, which you need to double check if you use a diode in your circuit. We are going to make our schematic nicer, more professional. I'm going to add some notes. So place text, left click, escape, select the text. I'm going to change it to USB for power only. I'm going to change the color and I'm going to make it a little bit bigger and maybe italic like this. And I'm going to add also some text up here about the battery connector. So I'm going to copy this, Ctrl+C, Ctrl+V, and we are going to change it maybe like battery connector is the text what we would like to have here. I'm going to squeeze this a little bit so we have more space for the rest of the schematic. By the way, it's important how you draw this selection. If you draw from the top left, then it will only select all the components which are inside of the square. But if you draw this selection rectangle from bottom right, then it will select everything what is also on the edge of the rectangle. So this time I would like to select only everything what is like here. So I'm going to move it a little bit up like this. And same here. I'm going to move it maybe a little bit down like this. What is also always very useful to have on your board is power LED. So go inside of library. We are going to find 0805 LED, maybe green color. Search for it. And be sure we are going to use a basic part. So this first one is okay. Left click on place, press spacebar to rotate, and put it inside of our schematic. Maybe it's somewhere like this. Escape. When you place an LED into your schematic, then together with LED, usually you also need to place a resistor, because this resistor will limit the maximum current which will flow through this LED. Okay, you cannot flow very high current through LED because you will damage this LED. And a little bit later I will show you how you can calculate this minimum value of the resistor, which you may need to use with LED. But for this power LED, when I calculated this minimum value of the resistor, the LED was like super bright. It was disturbing. And it means what I had to do, I had to actually try different different resistor values. I just desoldered one resistor and placed different one. And I found out that when we use 10K resistor together with this LED, then the brightness of the LED is just right. And that's what we are going to use in this schematic. We are going to place 10K resistor to limit the current which will flow through this LED. It's going to be super simple because we already have 10K resistor in our schematic. We can just select it, left click, Ctrl+C, Ctrl+V, and left click to place it. Connect the resistor to the power, connect resistor to the LED, and copy the ground symbol, Ctrl+C, Ctrl+V, connect it to the LED, and maybe move it a little bit down like this. Don't forget, the current through a diode can only flow one direction. So if your LED is rotated like this, it's not going to work. Okay, it has to be rotated like this because current only can flow from this side of diode to this other side of the diode. Now, a tricky question. Do you know why we connected this power LED to this +V USB? We could connect it to +V baud, or even better, we could connect it to this plus V in. And then power LED would be always on when our board would be powered. However, when you are using battery to power up your board, maybe you really don't want to waste the energy from the battery to light up this power LED. And that's the reason why it is connected only to this plus V USB, because in this case, the power LED will only turn on when your board is powered from USB, but it's going to stay off. It's not going to consume any energy when your board is powered from battery. So we place it here to save the power from the battery. We have finished our power circuit. We are going to make few small adjustments or tweaks. I'm going to make it a little bit nicer so it looks symmetrical. We would like to maybe add some notes that these resistors are not going to be fitted. I'm going to copy this, Ctrl+C, Ctrl+V. I will change the text to NF, like not fitted, and I don't want to make it so visible. Maybe use this kind of gray color. Okay, Ctrl+C, Ctrl+V. Oops, Ctrl+V, Ctrl+V. Okay. I'm going to add a title, Ctrl+C, Ctrl+V. Let's call it power and make it a little bit bigger. Use bold, no italic. Okay, and maybe move it a little bit down. Perfect. Next, we are going to connect this LED, and to limit currents flowing through these LEDs, we need to put here some resistors. And as I promised, we are going to learn how to calculate the value of these resistors, which we would like to use together with an LED. Select our LED. We would like to see the datasheet. So left click on View Datasheet. Open Datasheet. And the numbers which are important for us are forward current and forward voltage. When we have a closer look at like very simple circuit, how an LED is connected, it is going to look like this. There is some power, then we have a resistor and the LED. Now the voltage across the LED, we know this voltage. This is the forward voltage which we can see here, and it is different for different LED color. The voltage which is going to be across this resistor is basically the power voltage minus the voltage on this LED. And the biggest voltage on this resistor will be here when, do you know when? When this voltage across LED is going to be the lowest. So from these three numbers, the most important for us is this lowest 2.1 volt number. That's what we would like to use in our calculation. Then also this forward current 10 milliamps is important for our calculation. So remember these two numbers, 2.1 volt and 10 milliamps. Let's go back to our simple circuit, and I'm going to enable this next layer, which is telling us what we already know. Okay, so this is the voltage across the diode, 2.1 volt, and this is showing the current 0.01 amp or 10 milliamps, which we would like to have flowing through our circuit, through our resistor and through our diode. As I already explained, to calculate the voltage across this resistor is very simple. Basically, it is the input voltage minus the voltage on the diode. And in our case, the input voltage can be 5 times 1.5 volt. These are 5 1.5 volt batteries. And minus 2.1 volt, which is across the diode, it means the maximum voltage which we will have in our circuit across this resistor is going to be 5.4 volt. Once we know this voltage across this resistor, and we also know the current which should flow through this resistor, we can very simply calculate the value of this resistor. We can use this equation or Ohm's law, which says that the resistor value equals the voltage divided by current. So in our case, it would be 5.4 volt divided by 0.01 amp, and our minimum resistor which we can use together with our diode is 540 ohms. So this is the super simple way how you can approximately calculate what is the minimum value of the resistor which you need to connect together with an LED. Based on this calculated value, we would like to find our resistor. So what you can do, you can search for something like resistor values. I'm going to click on this table, and in this table you can see the basic standard resistors what you can normally buy. And in our case, we would like to use the closest resistor with higher value than what we have calculated. So we calculated 540 ohms, and the closest higher standard resistor is 560 ohms. So this is the resistor what we are going to add into our schematic. We are going to use same technique as we used when we were looking for 0 ohm resistor. I'm going to select an existing resistor. I'm going to copy manufacturer part number, Ctrl C, go to library, clear this, Ctrl V, and we are going to adjust this number, change it to 560 ohms, search. Okay, this is 560 ohm resistor. It is extended part, but it's okay. We need this one for our LED. So select it, left click, and place it into our schematic. Left click, zoom in, press space bar to rotate, and place it maybe like this, this, and this. Escape. When you would like to connect something in your schematic, you don't have to always use this wiring tool. You can simply just click on this pin which is here, and you can just start drawing the line. It is a little bit faster, yeah. Okay. One of the most common ways how to control LEDs is to use a transistor which is connected between this LED and resistor and the ground. And probably the most common transistor what is used for this purpose is 2N7002 transistor. So go into our library and search for 2N7002. 。  7002. As you can see, this is the basic part, so just left click, click on place, zoom in, place it here, then we need also another one here, and the third one like here, escape, connect them together with the resistors, escape, and we need to connect this transistor also to ground, so copy ground symbol, Ctrl C, Ctrl V, Ctrl V, Ctrl V, and connect it. I'm going to make it a little bit nicer. I'm going to move this little bit away from each other so there is a little bit more space. I'm going to select this, press Ctrl, hold it down, select also the transistor, and just move it. And same here, select this, press Ctrl, hold it down, select also the transistor, and move it like this. I'm going to draw short lines which will be connected to these gates of the transistors, and then we will name these lines or these connections. To name them, we would like to see which of these LEDs is red, which is blue, and which is green. So select it, edit symbol, and show these numbers. So yes, 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 okay. This is pin number 2, 3, 4. When we go into datasheet of the LED, we can see pin number 2 is red. So this is the red LED, and we would like to name this maybe like LED R. Pin number 3 is blue LED. So click on this net label, left click here, escape, left click to select it, and change it to LED B, enter. And the last one, pin number 4, will be the green LED. So again, what you can do, you can click here, or you can simply just copy this, Ctrl C, Ctrl V, and change it to green. Select the LED, edit symbol, and hide these names or numbers again, because they don't look very nice in this symbol. Okay. Now, my question to you is where to connect this pin of the LED. Do you know? We could connect it to the battery voltage, or this USB voltage, or to plus V in, or 3.3 volts. What would be the best way to connect this? We don't want to connect it to the battery or USB, because then it would only work when the battery would be connected or when the USB power would be connected. So we could connect it to plus V in or 3.3, but there are two reasons why we don't want to use 3.3 volts. The first one is that it can be quite low voltage. If you remember, the forward voltage for these LEDs is 2.1, 3.1, and 3.0 volt. So this means that this green LED, it may need at least 3.1 volt to be able to work. So 3.3 volt as a power supply may not be the best option. And also we really don't want to drive high current through this LDO, because on this LDO there will be some losses. So, and the losses, it means we would just waste energy from the battery. So maybe the best way to connect our LED is use this plus V in. And that's where I'm going to connect it. Or that's where we are going to connect it. Left click on this V in symbol, Ctrl C, Ctrl V, place it here and connect it. When we have a look on this our finished LED connection, you may notice it is a little bit different from what we calculated here. Okay, this is like super simple connection, just power, resistor and LED. In our board, the power goes through this diode. There will be some loss, like, I don't know, 0.5 volt. Then it also goes through these transistors. There may be some voltage loss across these transistors, but our calculation is still good enough to use the values of the resistor what we have calculated. The currents are not going to be higher. There will be actually, in this real circuit, they may be actually a little bit lower, because the final voltage across the diode plus resistor may be a little bit lower than the 7.5 volt what we use for the calculation as the power input from these batteries. Okay, I just wanted to point out this, that even we use like super simple calculation, this calculation is still like good enough for what we needed, good enough to calculate the resistor value for this LED. Now, you may be asking, like, why we had to use these transistors to control these LEDs? Could we maybe connect these LEDs directly with our microcontroller? In some cases, yes, you can control LED directly with the pins of the microcontroller, but you need to know what you are doing. Okay? Anyway, even if you know what you are doing, as you can see, even I have used in this our schematic this kind of connection, because this is much more standard, and this kind of connection is much safer. It is the easy way how you can control all the kind of components or devices which may require even higher currents than what you can drive with microcontroller directly. And also, when you use these transistors, then you can basically power up these devices or components from all the kind of different powers, and you don't really need to think if this power is going to influence somehow your microcontroller or not. Okay, so this kind of connection is much safer, and I use it a lot to control something or anything through the pins of the microcontroller. I almost always use these transistors, even when I drive LEDs. I'm going to open datasheet of this transistor. Left click, view datasheet, open datasheet, and we are going to have a look how this transistor works. So I'm going to copy this MOSFET N channel. That's what we are using, Ctrl C, and I'm going to search for something like this, and maybe add switch simulation. When I scroll a little bit down, here, left click, then This is a very nice article where you can learn how the transistor is going to work. But basically, when the gate of our transistor is going to be connected to 0, then the transistor itself will behave as a open switch. So basically, when this is going to be 0, it means this LED is not connected to ground. However, if you connect the gate of the transistor to power, then this transistor is going to be like closed switch. So in our case, when we connect power, for example, when the microcontroller set output to high, then this transistor will open and it will make connection between this resistor and the ground. So it means the current will flow through our LED and it will switch on LED. Okay, if you would like to know more, then you can read this whole article. If you would like to choose your own transistor for your own board, there are a couple of numbers which are important. So when we go into datasheet of the transistor, this is what you may need to double check. So first, you would like to know what is going to be the maximum current which can flow through your transistor. Okay, in this case, it is 0.115 amps, so 115 milliamps. It is enough for our application. The maximum voltage between D and S is 60 volts. We have like 7.5 volt, that's okay. Maximum gate source voltage plus minus 20 volts, that's the voltage what you can put on the gate. But what is more important is this gate threshold. This is basically the voltage what you need to apply on this gate to open the transistor. So it is like 2.5 volt. We will be using 3.3 volt, that it's fine. And also drain source on resistance. This is the resistance which you will have between D and S when your transistor is open. And this resistance, it depends on the voltage which you apply on the gate. So for example, if on the gate there is like 5 volts, then the resistance in your transistor can be like as high as 7 ohms. So this could be then like 7 ohm resistor. Okay, so these are the numbers which you may want to double check when you will be using your own transistor in your own board.